Today we're doing day 86. We're going to do the direct comparison test and the limit comparison test. Let's review a little bit what we covered yesterday. Remember that this next set of lessons is dealing with the convergence test. So we looked at the nth term for divergence. This could only diverge when the limit as n approaches infinity is not equal to 0. It does not say anything about convergence. And I put a little note right here in case you didn't recognize. There's a little note right here that kind of reminds you of that. It only tells you ideas about diverging. The geometric series test, this is where the ratio is going to be less than 1, is converging, ratio greater than 1, diverging. It's when you have the ratio raised to the power of n. The ratio test is related to the geometric series test, so you'll find that the ratio conditions for converging and diverging is similar. The ratio less than 1 is converging, the ratio greater than 1 will be diverging. The p-series test happens when you're dividing by 1 over n to the power. When p is greater than 1, that's going to converge. When p is less than or equal to 1, we have diverge. Notice that these four right here are opposite, I guess you could say. Yeah, that makes sense. Opposite of these two right here. Okay. Today we're going to be studying two more. We're going to be studying these two, which is the direct comparison test and also the limit comparison test. So the direct comparison test, a couple things that we need to keep in mind with the direct comparison test is that we're going to be using an object, a person, a star, whatever you want to use. And the idea is that if it could go through the door, we say it converges. If it doesn't go through the door, we say it diverges. And we'll draw pictures to help us understand this, okay? But the technical writing for this is that if what you're comparing is bigger than the original problem and the bigger one converges or go through the door, then the original problem, which is smaller, should be able to go through the door or converge as well. The condition for diverge works the other way. If the one that you're comparing to is smaller than the original, and that the smaller one cannot fit through the door, or the small one diverges, then the bigger or the original one can't also fit through the door. Okay. We do have two conditions where they're IDK. I don't know. They're inconclusive. When that happens, we use the limit comparison test only when the direct comparison test fails. So the only time you should be thinking about this is if the direct comparison test does not work. So here's how we do it. We take the limit of both of them. We take the original series and the second series. We take those formulas, we divide them, and we do the limit. If the limit is a positive number, you'll notice they're the same. Then what that means is that the original and the new series will behave the same. So if the one you're comparing to is converging, so will the original. If the one you're comparing to diverges, so will the original. Only if this limit is equal to a positive number. Okay, so we'll take a look at this. A couple things to keep in mind here that you need to remember is that in order to make a comparison, you need to know which one is considered to be bigger and which one's considered to be smaller. So, for example, 1/2 and 1/5, we will say that 1/5 is the smaller denominator. And the way that you want to look at this is you want to compare these two words, like, let's see, smaller and bigger, okay? So when we look at the denominator, and I'll be saying this very carefully, when you look at this denominator compared to the other, what is this denominator, bigger or smaller? We say the denominator is smaller, so the fraction will be bigger. Okay, and it works the other way. This denominator will be bigger, so this fraction is actually smaller. It doesn't matter which one you pick, but you just have to look at one of them and decide which one's the bigger one. Once you decide which one's the bigger one, the other one has to be the smaller one. Okay. Next thing, we talked a little bit at the end of pre-calc last year about the principle of dominance. A little bit of a preview is kind of like this. If I have n squared divided by n and I take the limit as n approaches infinity, we say that this is top dominant. And the reason why this is top dominant is because the one at the top grows faster than the bottom. For example, if I plug in 1 here, that's 1. If I plug in 2 here, that's 4. If I plug in 3 here, that's 9. If I plug in 1 here, that's 1. Nope, just kidding, that's 2. Plug in 2 here, that's 3. Plug in 3 here, that's 4. We say the top is dominant because the polynomial at the top grows faster than the bottom. When the top is dominant for any limit, this limit is going to be either positive infinity or negative infinity. Okay? The other one that we looked at was what happens if it's bottom dominant. So for example, if I have n divided by n squared plus 1, and if I take the limit as n approaches infinity, yes, we could use a shortcut here, but we're trying to show you guys a different way to kind of evaluate this limits. The bottom is dominant because it grows faster than the top. For example, plug in numbers to the top, it's 1, 2, 3, 4. Plug in numbers at the bottom, it's going to be 1. No, plug in 1, you get 2. Plug in 2, that's 4 plus 1 is 5. Plug in 3, that's 9 plus 1 is 10. You notice that this is already growing faster than the top. When the bottom is dominant, this limit is automatically 0. And that's me not using any other rules that we've used before. This is just talking about what top dominant means and bottom dominant means. The reason why we talk about this is because now we're going to move away from polynomials and we're going to be looking at, well, what happens if I have log of n at the top and if I have n factorial at the bottom. We don't know any tricks about this, but I do know that n factorial is the dominant, it will grow faster than the top. Okay, and you can plug in numbers to verify this. And so without even doing any tricks, since the bottom is dominating over the top, I know this is automatically 0. Another example could be something like this. What if I have, let's say, n squared plus 2 and I have 3 to the n? Okay, you could use, you could try to, well, no, actually, we're going to need to talk about the dominance. The top is going to be growing faster than the bottom because exponential grows faster than the bottom. So, for example, if I plug in numbers, that's 3. Plug in 2, that's 9. Plug in 3, that's 27. Plug in 1, that's 3. Plug in 2, that's 6. Plug in 3 squared is 9 plus 2 is 11. You already notice that it's growing faster at the top. That means that this limit is automatically going to be positive or negative infinity, and you decide that by just plugging in a big number here. Okay? So, we did look at this already with polynomials. Now we're going to extend it. I want you guys to go ahead and take a look at this and take a moment to kind of try to just get an idea of what the order is. One way that you could figure out the order, if you didn't memorize this kind of the order that you see here, is just plug in numbers. If you're not sure which one dominates the other, just plug in numbers and see if the top is dominant, the bottom is dominant, and if you're not sure, try to look for a different limit rule to figure this out. Okay? So if you notice, factorials always dominate everything else. That's the fastest growing function. Exponential is next, then polynomials, then logarithms, then numbers. There's more functions we could put in here, but these are the ones that are the most. These are the ones that are the most used. Okay, got a lot here. Let's go ahead and just get into it. Let's start with the direct comparison test, and start with this example. Okay. Here we have the sum of 1 divided by 4 to the n plus n. I have no rules or anything that could work this out. If I did try the ratio test, which I do think some people will think, oh yeah, it's a combination. If you did try the ratio test, it will be inconclusive. Okay, so here we're going to use the direct comparison test. Now whenever you make a comparison, you're going to compare by dropping whatever, or let me start over. You're going to compare to something and keep whatever is going to be dominant. Keep whatever is dominant. So remember that list. This is polynomial right here. This is exponential. Exponential is the one that's more dominant than polynomial. So what I'm going to do is I'm going to get rid of this n. Don't really cross it out, but that's what I'm going to be dropping here. So I'm going to compare it to 1 over 4 to the n because I want to keep the dominant function. Okay. Next thing I'm going to do is I'm going to figure out who's bigger and smaller. So I'm just going to look at this denominator here. I'm going to ask myself, is this denominator bigger or smaller than that denominator? We're going to say that this one is going to be smaller. Just because I'm adding n here, so that should make it bigger, and there's no n here, so that should be smaller. Or you could plug in a number. If you're not sure, plug in a number. If I plug in 1 here, that's 4. If I plug in 1 here, that's 4 plus 1. You can see that this denominator is going to be smaller. Okay? So if the denominator is smaller, what do we say about the fraction? That means this is going to be the bigger fraction. This is going to be the smaller denominator. Now that we figured out who's bigger and smaller, let's run the test on the right side. This is going to be geometric series. I notice that the base of the exponential is going to be 4, but since it's in the denominator, we know that the ratio is going to be 1 over 4. This 1 over 4 is going to be less than 1. We're going to say this is going to converge. Okay, so let's make a story of just this, okay, of just this. The bigger converge, which means there's going to be someone that's bigger. Draw a tall person here. Converge means you fit through the door, so you have to draw the door. That's one example of the door. You could draw more if you like, but you always try to make the story with this idea, with the converge-diverge idea. Okay? Next, once you have that story right, see if the smaller one either fits or does not fit, no matter what the size of the door is going to be. Well, if the big person can fit through the door, the small person has to be able to fit through the door every single time, no matter what door we're talking about here. So this one is going to converge always by the direct comparison test. Okay, let's take a look at the next one. This one looks like, and this is what you're going to think, this kind of looks like p-series. This kind of looks like p-series. P-series is 1 over n squared plus 1 over n squared. I remember that yesterday we talked about this idea about that, hey, Mr. Fontan, yesterday you said that if it was sum 5 divided by n squared, you could still use p-series. Why can I still use p-series here but not here? And we talked about the idea that you could factor out the 5 outside of the sum, and now it becomes p-series. In this example, you cannot factor out a plus 1. We've never done that before. For example, if I have 3n plus 2, we have never took this 2 magically come out of here and call that 3 to the n. That's a multiplication division property. You do not apply it to binomials like this. Okay, so the only way that we could get rid of that plus 1 is going to be, let's make a comparison. Now we talked about dominant functions again. You could use that concept as well when you're trying to figure out what to compare to. Who grows bigger, numbers or polynomials? Polynomials grow fastest, so we're going to go ahead and get rid of the 1. That's another way to look at what should I be dropping here. So sum 1 over n squared. Okay, we pick a denominator. This time I'm going to pick this denominator, and I'm going to ask myself, is this bigger or smaller than the other denominator? This denominator is going to be bigger, so the fraction, so the denominator is bigger, so the fraction is going to be smaller. So this is going to be small, and this one's going to be big, or bigger. Okay, then we ignore the original problem when we just run the test here. This is p-series. P is equal to 2. That's going to be greater than 1. This one's going to converge by the p-series test. We go ahead and make a story for the right side for the comparison, right? Bigger person looks like this. Converges means I go through the door. Once I get the story right, then you draw in the original smaller and ask yourself, does he also fit through the door? And he does, no matter what door. As long as big brother could fit, little brother could fit, right? So we're going to say this person is going to converge. Okay, a couple more. Let's look at this one. We did look at this a little bit last year, but we got to probably rewind you a little bit again. What I see here is a cosine squared of n. I'm not sure what that is, so I might be thinking this is probably what I dropped, just because I don't know what it is. That's not always the reason why you want to say, but that at least gives you a hint of where you might want to start your reasoning. This n right here looks like p-series, right? So maybe I could probably keep this and run a p-series test here. We're going to go ahead and make a comparison. And I'm going to use the concept that I want to keep the dominating function here. We're going to say that n is going to be dominating over cosine squared of x, because if you remember on the unit circle, cosine is only going to be the x coordinates on the unit circle. If you take a look at all the x coordinates on the unit circle, what's the biggest x coordinate you see here? It's 1 and negative 1. So cosine squared, if you square the 1 and negative 1, the biggest this could be is 1 or negative 1. If I plug in 2 into both of this already, this 2, and if I plug in 2 into here, that does not get bigger than 1. This is already bigger than that. So keep that in mind. That's something that I shared with you last year. I'm bringing it back again. Sine and cosine, the biggest that they could be is just 1, and typically this is weaker than most functions. Okay, so we're going to go ahead and drop the weaker function, which is cosine squared of n, and we're going to keep the dominating function, which in this case is going to be the polynomial n. So we're going to say this is 1 over n. Okay, let's look at the right denominator. Is this denominator bigger or smaller than the other one? Seems like it's bigger because this n is being subtracted from this. You're taking more away from this n, so this has to be smaller and this has to be bigger. If this denominator is bigger, that means that the fraction has to be smaller. And then that means the other fraction has to be bigger. Okay, let's run the test. We said this was p-series. I'm going to let p equal to 1. That's going to be less than or equal to 1. This will diverge by the p-series test. Let's go ahead and make the comparison, smaller and diverge. So I'm going to draw a small, we'll do a lady this time so that we could be inclusive here, right? And then we go ahead and just say the small person cannot fit through the door. That's what diverge means. So I'm going to go ahead and draw a door just like this. She cannot fit. Now that I got the story right, let's go ahead and talk about bigger person, big lady, right? And so does she fit through the door? No, she does not. So she does not fit through the door no matter what door I draw, right? As long as this story is right, you got to make sure that this story is right. Even if I draw a smaller door or a slightly bigger door, you got to draw doors that they can't fit. So the big lady diverges. Okay, next, letter D. Let's keep going. Here, be careful here. It's kind of like a trap. Just because we're doing direct comparison test here doesn't mean it's always direct comparison test. For example, I guess you could make a comparison test to this, right? But why would you do that? Instead, let's just take out that 2, or you could leave it there and just recognize that, you know what, this isn't really a comparison test because this is actually p-series. Okay, so remember that if you could factor out numbers, that's one way of eliminating numbers that you don't want in there. But if you're adding or subtracting numbers, there's no way you could factor those out, so that's probably where you do the direct comparison test. Here, you don't need it. Okay, just run the test. This is going to be p-series. Let p equal to 1/2. It's going to be less than or equal to 1. This is going to be diverging by the p-series test. Okay, so this is what we went over last year. Hopefully this is a nice reminder of how you deal with this. Let's go into some new stuff with the limit comparison test. Okay, we're going to start with this first. Now here's the thing about the limit comparison test. The limit comparison test, you don't ever go through this right away. You should always try the direct comparison test first. Always try the direct first. If that fails, then you go to the limit comparison test. Okay, so for these problems, even though I know this is limit comparison test, you will have to start these problems doing the direct comparison test just like the last example. So let's just go through it again. Okay, so we're going to make a comparison test here because I cannot factor out the n. But I do know that 4 to the n is dominating over the polynomial n, so I'm going to keep 4 to the n, and let's just drop the polynomial n. This is going to be sum 1 over 4 to the n. Okay, the ratio here is going to be, I keep the base of 4, but since it's at the bottom, we're going to call that a ratio of 1 over 4. This is going to be less than 1. This is going to converge. Okay, let's make the story. Oh, I didn't decide who's big and small, right? Okay, let's figure out who's big and small. This denominator looks like it's bigger than that one. So we're going to say that this is going to be small right here. This person's going to be big right here. Okay, this time I'm going to draw a star. A small star converges. Means I fit through the door. What does it say about big star? And the way that I drew it, though, it seems like big star cannot fit through the door. But wait, doesn't this door right here match up with this story right here? Remember, the door and the person, all of that goes with this story. And if I draw that door, that one could also work for the story. But big star can go for that, but big star can't go for that. So it depends on the door. If ever you did that last year, we said this. I don't know, or we could say it's inconclusive. Now that it's inconclusive, this is when you start the limit comparison test. So here's how you run the limit comparison test. You need to calculate a limit as n approaches infinity of a sub n divided by b sub n. Okay. So this is going to be limit as n approaches infinity. I haven't done the limit yet, so please write that again. We write down a sub n. The a sub n is whatever the original series formula is going to be. So it's going to be 1 divided by 4 to the n divided by 4 to the n minus n. I'm just rewriting that. B sub n is always is the one that you're comparing it to. So this is 1 over 4 to the n. Let's write that a little bit better. 1 over 4 to the n. Okay. Then I'm going to calculate this limit. I'm going to do keep change flip here. Okay, this is equal to limit as n approaches infinity of, this is going to be keep 1 over 4 to the n minus n, change, and then flip 4 to the n divided by 1. Okay, this is going to be limit as n approaches infinity of, we multiply across, 4 to the n divided by 4 to the n minus n. Okay, this is a limit that we've actually never seen before because it's a combination of polynomial and exponential. But keeping in mind of what we talked about earlier, you really want to use the dominating ideas here. Who's dominating more, the exponential or the polynomial? So since the exponential is dominating more than the polynomial, I'm going to try and use the exponential rule here. Okay, from pre-calc, especially in the chapter 12 that we did last semester, I remember that the rule for the exponential is that we want to divide by easy exponential for all of them, for all the terms. Okay, so I'm going to divide all of these by 4 to the n, 4 to the n, even this one 4 to the n. Here's what I have, limit as n approaches infinity, that's going to be 1 over n divided by 4 to the n. Okay, now we do the limit. I'm going to evaluate the limit here. If you just substitute this, you're going to get infinity over infinity not okay, so you need to think about some other rules that you have. And we just talked about this, about the principle of dominance, right? So if it seems like that 4 to the n in this fraction is dominating over the n at the top, so we say that this is bottom dominant, right? So the bottom grows faster than the top. It's like this problem, right? When you say n divided by n to the third plus 3, we know that this limit is always going to equal to 0 because the bottom is dominating over the top. So same thing here. For this specific limit right here, since I know the bottom is dominating, automatically this limit is going to go to 0. Okay? So that's a little bit new. Just keeping that in mind, it's something new. I'm going to bring it up again to remind you guys how to do that kind of a limit. So what's left is going to be 1 divided by 1 or 1. More importantly, this is a positive number. Now let's look at this again because we haven't seen this last year. Since this is going to be a positive number, that means that if one of them converges, the other one converges. If one of them diverges, or the other one diverges. Or they just behave the same. So positive number means behave the same. So now we go back to the original problem. Now I'm coming back. I'm going to go over here, right? And I'm going to erase this IDK, and I know now. If the one that I compared to was converging, I know that this will also converge because the limit comparison test tells me that if it's a positive number, they will behave the same. Okay, that's the limit comparison test. Let's do a couple more. Okay, part B. This one, well, what can I do here? Let's do a comparison again. Let's double check. So I'm going to compare this to, what am I going to drop at the bottom? N squared is dominating over 1, so I'm going to drop the 1 and keep the n squared. So I'm going to say sum n divided by n squared. I realize I could simplify this. That's the same thing as sum over 1 over n. Okay. So if I take a look at this 1 over n and 1 over n squared plus 1, who has the bigger denominator? It's going to be this one. So if this has the bigger denominator, this will be the smaller fraction. So I'll get small right here. This is going to be big right here. Let's run the test for big. This is p series equals 1, less than or equal to 1. This one's going to diverge. Let's create the story for this. Big diverge means a big person cannot fit through the door. Let's just do a circle. Sure. Big person cannot go through the door, so there's that. What does it say about the small person? Depends. In this case, small person could fit. But if the door was actually here, right, as long as you get this story right, you're okay. And you got to consider all the types of doors that will work for the story. Seems like the small one will fit, and it depends. I don't know. So if you don't know, because it depends on the door, you go straight to the limit comparison test. Limit. As n approaches infinity, you take one of the formulas and you divide it by the other one. Okay, so the original one was n divided by n squared plus 1, and you divide it by, what did I compare it to? 1 divided by n? Oh, and I forgot the limit. Don't get lazy, I got lazy there. Okay, keep, change, flip. So limit as n approaches infinity of keep n divided by n squared, n divided by n squared plus 1 times n over 1. If I multiply this across, I get limit as n approaches infinity of, that's n squared divided by n squared plus 1. This is the highest power idea for polynomials, so I'm just going to keep the numbers in front. That's 1 over 1. And that's going to be just 1. More importantly, this is a positive number. Since this is a positive number, this tells me that they will behave the same. So now I go back here. And I say that since big diverged, the direct comparison test didn't work, but the limit comparison test tells me they behave the same. So if they behave the same, this one should also diverge. Okay, a couple more. Letter C. Let's do another comparison test here. I'm going to compare two. Sum. Let's see, what am I going to drop here? Polynomial or the number? I'm going to drop the number here because polynomial dominates over the number. So we're going to say 1 divided by square root of just n squared. I could simplify this a little bit, and I'm going to say this is 1 over n. Sum 1 over n. Okay, looking at the denominators, who has the bigger denominator? It seems like the right side does, so this one will get small for the fraction, this will get big for this denominator. Let's run the test. P is equal to 1, less than or equal to 1. This is going to diverge by the P-series test. Small diverge means small person can't fit. Wait, that's wrong. Small person can't fit. What does it say about the big person? Can't fit either. No matter what door you draw, as long as the door matches up with the story, that big person cannot fit. Diverge by the direct comparison test. So this case, we didn't need to go to the limit comparison test because the direct comparison test was enough. Okay, letter D. Letter D. All right, letter D. We're going to make a comparison test here. Okay, I know some of you guys are wanting to take the limit, but remember, if you take the limit of this, you're going to, as n approaches infinity, that limit is equal to 0. Doesn't say anything, right? Because the highest power is 5, so the bottom is dominant. It's equal to, the limit's equal to 0. Doesn't really say anything as far as the convergence test goes. So we're going to make a comparison test. Now here is an example where you could actually drop multiple ideas. You want to keep whatever's dominant. At the bottom, the only one that's dominant is really n to the 5th. Everything else, who cares? It's whatever, right? So at the bottom, I'm going to keep n to the 5th here. And I'm also going to keep, let's see, at the top, I'm going to keep whatever's dominant, which is just n to the 3rd here. Okay? If I simplify this, this is sum over 1 over n squared. Okay, we let p equal to 2. This is greater than 1. This is going to converge. Okay, if I compare this denominator with this denominator, it seems like that this denominator is going to be smaller, so this is going to be bigger. Okay, so bigger converges means big person, big lady converges. What does it say about small lady? Also converges. Right, also converges no matter what size door it is. So this is one example where maybe you don't drop just one thing. You could drop more than one because there's multiple terms here. If you notice, this is kind of one of the first ones that we saw that there's actually 3 terms. Everything else is like 2 terms. So we only had a choice to drop just one thing, but you could drop more than one, especially if there's more than 2 terms in a problem just like this one. The concept is that when you make a comparison test, you want to keep the dominant polynomials, the dominant functions for both the top and the bottom, if you can. Okay, let's put it all together now. So now that we looked at those two, let's take a look at these. Think about what test. Okay, this looks like geometric series, but wait, there's a +1 here. I cannot just factor out this +1 here. You can't. You could factor out the 5, which would let you use geometric series, but this +1 is an issue here. Since you cannot factor out the +1, the only way you get rid of it is that you have to make a comparison. So we're going to drop the +1 and just keep the dominating 5 to the n. This is going to be 5 divided by 5 to the n here. This denominator is going to be smaller, so the fraction is going to be bigger. This is going to be small. Okay, and then we run the test. This is geometric series with the base of 5, so the ratio is going to be 1 over 5 because the 5 is at the bottom. This is less than 1. This will converge. When big converges through the door, what does it say about small? Also converges by the direct comparison test. Okay, take a look at part B. Okay, what test for part B? This is P series. P is equal to 3, greater than 1. This is going to converge. Right? That 10, you don't need to make a comparison test because you could factor it out, and it really is P series. Okay? So yes, converge here. Look at the next one. Okay, what test? And I'm asking as if you could give me an answer and I'll listen, but I'm not really not. Okay, here we go. This is going to be, I suspect, wait, I know my eyes here could tell me what this is. I know what this is. This is a limit. The limit as n approaches infinity of 5n divided by 1 plus 2n. Is this is highest power. I know that this is not going to be 0. That's not 0. Diverge by the n-term test. Okay, and remember the n-term test, the only way you know that is that you've been looking at limits for so long already that now your eyes have to be able to recognize, I know the answer to that limit. It's not 0. Okay, let's go to letter D. What test?
Looks like it's p-series, but there's a +1. I can't really just drop the +1. I can't factor it out, so we're just going to do a comparison test. Let's compare. I'm going to go ahead and compare this to 1 divided by n to the 2/3. Let's compare the denominators. This denominator is going to be smaller, so we say the fraction is going to be bigger. This is going to be small. Okay, run the p-series test. P is equal to 2/3. This is less than 1. This is going to diverge. Let's make the story. Big person cannot fit through the door. What does it say about small person? Depends. Depends on the door. So now what we're going to do here is we are going to go ahead and do the limit comparison test. We're going to say limit as n approaches infinity of, take the two series and divide them. This is 1 divided by n to the 2/3 plus 1 divided by 1 over n to the 2/3. Okay, we keep, change, flip, limit as n approaches infinity of, keep, which is 1 over n to the 2/3 plus 1, change, and then flip n to the 2/3 over 1. Okay, we keep going. So now this is going to be limit as n approaches infinity of, this is going to be n to the 2/3 over n to the 2/3 plus 1. This is actually, you could actually use a polynomial idea here. Okay. We can use a polynomial idea here. Both top and bottom are not dominating each other, so I'm just going to keep the numbers in front. This is 1 over 1 or equals to 1. This is going to be positive. Okay, this is a positive number. So now that I found that the limit is a positive number, I'm going to go ahead and say that they behave the same. So if one of them diverge, that means the answer for this one is also going to be diverged by the limit comparison test. Okay, last one, letter E. I see factorial here, and automatically I'm thinking about ratio test, right? So let's go ahead and do the ratio test. I'm going to circle the n's that we have here. I have 1, 2, and 3 n's. I'll use different colors just to make sure that we're separating them. Okay, so now I'm going to say limit as n approaches infinity of absolute value a sub n plus 1 divided by a sub n. You have to calculate the limit, the ratio. This is equal to limit as n approaches infinity of. Let's do the shortcut. The top is n factorial, so we change the top, n plus 1 factorial, divided by, keep the original at the bottom, times. The bottom left is 10n, so I'm going to change the bottom 10 times n plus 1, and then keep the original at the top. The bottom right, in the green, is going to be n plus 2, so I'm going to write n plus 1 plus 2, which is really n plus 3. Keep the original n plus 2 here. Okay. Next step, once you write this down, is that you simplify. So limit as n approaches infinity of, let's see, for the factorial here, it seems like n plus 1 is bigger, so I'm going to expand that out. We'll call that n plus 1, and then we multiply by the next one. By subtracting 1, we get n. They match. We put factorial, cancel, cancel, that's 1 and 1. This is just n plus 1 here. This one is going to be, remember, I haven't done the limit yet, so don't do the limit rule. I'm just going to, let's just distribute that 10. So I got 10n divided by 10n plus whatever, even though I know that's 10, but I'm already looking ahead and knowing that this is going to be one of those limit rules. This next one is going to be n plus 2 divided by n plus 3. Do not say that this is 1 yet. You haven't done the limit yet. Okay, let's do the limit here, here, and here. Okay, this limit is going to be infinity. This limit is, keep the highest power, 10 divided by 10. This limit here is going to be 1 and 1, but infinity times anything is going to be infinity. This is the ratio, greater than 1, converge. Just kidding. Diverge. Okay. All right. I do want to show you one more thing here. I'm going to do letter E again, and you could write this down or you could just watch if you'd like. Since you guys understand the principle of dominance now, and that it doesn't only apply to polynomials, like this is 0 because the bottom is dominating, right? Or n to the third because n squared here, if I change it, this would be infinity because the top is dominating. Since you could apply that with any functions, maybe you can recognize that I could actually do this with the nth term. So let's do the nth term test. Let's take the limit as n approaches infinity of n factorial divided by, if I distribute this is going to be 10n squared plus 20n. I know that n factorial is the most dominating function. It dominates over the polynomials, so we say that this is top dominant, automatically I know this limit is going to be infinity, not 0. So this is another way that you could have gotten diverged without going to the ratio test. Okay, but I know there's something new, so we'll see if you guys just keep that in mind so that you could kind of pay attention to top dominance, bottom dominance when you guys start working out other problems. Okay, so that's it. Try those problems. I'll be back on Monday, and then I'll take any questions you have, or you could hit me up on Teams, and I'll try to respond as fast as I can. Okay, have a good day. See you guys later.